Okay, so I'm going to try to slap together a pre-lab and background for you here. Well, which is basically what pre-labs are all about, is to get you ready to go. And so we're going to be doing motion of a pendulum. So we're going to study two types of pendulums. Perhaps we're going to observe behaviors of what's so-called coupled pendulum, but basically we're going to be looking at this one here on the in the middle with this little doodad, excuse me, down here. That's called a bob. And then this disc, this rotating disc, which is pretty cool. They call it a physical pendulum. And then we're going to be taking some data. We'll do some graphing and fitting, which we've already had a go at. And then to study the motion of the physical pendulum, it involves this scary thing called an elliptical integral. But we're going to, oops, that's not all on your screens. We're going to compare data to an elliptical integral to test whether or not our pendulum actually matches up to the equations. And this is what physics is about. You have a back and forth between experimentalists and theorists. So what you need then, after objectives, you need to make definitions of these terms. And then we're going to study how length, mass, and amplitude can affect the period, capital T, of a pendulum. And also, in the case of these pendulums, amplitude is expressed in terms of an angle theta. So make sure your logbooks have something that explains that. So we can make these schematic drawings of our two, the simple pendulum, which is like the grandfather clock, and the physical pendulum, physical. So what we can, and I don't know if you've gotten that far in 2100, we certainly have it in my 2100 section, but we have a string, we have some angle from some resting point if we just sort of hang this down, or it's also called the equilibrium point. And so theta is characterized as the amplitude, and it's with respect to the resting point. So we could have positive theta and we could have negative theta. This is theta equals 0. And so if we make a free body diagram of that mass, we have the weight of it, and we have the tension of the string. And so then this is the real forces. So one can imagine that we can have a force, the T in the, say, y direction. Perhaps there is a component of weight. No, it doesn't look like it. But there is a component in the this would be x, y direction. And so what happens is that we can imagine at the top, say at the top, it's right. And then also, don't forget, there is also this idea that we can have a height, and you're going to learn about gravitational potential energy equals to mgh. So we can make a relationship between these two, the height, there's a potential energy, there's a kinetic energy here at the bottom. It's all kinetic energy here. It's all potential energy here. So there's different ways to attack this thing. and I don't want to get too much into it, but what this is an example of is a restoring force system. So that means that if I have a positive theta, I get a force in the negative theta direction. F is in the negative theta direction, and vice versa. If I have a negative theta, then the force is in the positive theta direction. So it tends to want to bring it back to the middle. And so what that means is that you get, you can create an equation of motion, theta equals cosine and some a cosine of omega t, which omega is defined as theta radians per second, right? So it's an angular speed. So, but you can also say that omega is equal to 2 pi times the frequency, and the period equals 1 over the frequency. So these are pretty broad brushstrokes, sorry. This is all part of your lecture class, but we can still, and I don't know why we're doing this lab now, but this is what the boss says, this is what we do. And let's see, we need a new slide. First of all, let's paste that here. And let's just make a few more just in case. All right. So it turns out, and this is in this manual here, that we can derive an equation for the period. And that says the period is equal to 2 pi. Notice the 2 pi because this is related to the omega I mentioned before. And the L over G comes from the free body diagram. And G is an acceleration. And so if you don't know already, you have this equation, Newton's second law, and F equals ma. And coupled with all the concepts of F equals ma, the free body diagram, and the restoring force, you get what's called periodic motion, simple harmonic motion. Now, one thing here too, we're going to investigate that this uses this small angle approximation. And what that just means is that for us is that it only is valid for some range of thetas, which we're going to find out. I think it's really not, it can go pretty high. I think theta has to be less than about, in fact, theta has to actually be less than about 10 degrees. That's right, we figured this one out in past semesters. But we're certainly going to explore thetas larger than 10 degrees. All right. So now for the, so we're going to be studying, we come up with an equation here. And so we're going to study the effects of L and G. We're going to study the effect of M, but, hint, hint, nod, nod, whatever. Since there's no M in this equation, we don't expect it, right? So I'm expecting to see that you're writing the things down, right? Basically, we've got a system, and this is what it looks like. This is sort of some parameters of it. I don't expect you to derive the formula here. It's too early in the semester. So we're just going to say, look, we have this system. We have the existence. It looks like we have an existence of a restoring force. That means we expect periodic motion. That means we expect that there's a frequency. If there's a frequency, then we should have a period. because period is equal to 1 over frequency. And at the end of the day, the theorists have given this equation to us. Now we want to see if this thing actually obeys. So we'll get to procedure in a moment. I'm looking over at my notes here. And oh yeah, part of it is that we assume the string is massless. Well, I'm going to throw it out there, but it's not critical, and it is critical to the calculations, but it's not to the derivation. But it's not critical for us in this lab. And basically, what that means, mass of the bob, or the I forget what you call the end of the pendulum. I think bob is really much greater than the mass of the string. And of course, the string is this here. And don't forget, you have to describe the apparatus. That's part of the lab, but we do that when we're in person, when we're in the room. Okay, let's see. Looking at my notes. All right, this is procedure here. So first, let's finish up the background. So now we have the physical pendulum. So what happens in the physical pendulum, you have an aluminum disc, so you can't say that there's a point mass involved. So when you had the regular pendulum, you could say that you had yourself a point mass, and that doesn't work out. It's not, well, it can be done, but you have to be a little clever. Excuse me. And the way you do that is by using the moment of inertia, which you don't know about yet. I don't understand why we're doing this lab. The moment of inertia and with the so-called parallel access theorem. And this is what you'll be doing at the end of the semester in 2100. And by using that, at the end of the day, you come up with this expression here. And so the T, in this approximation, the period of motion is given. Notice that the disk is massless. It becomes, if the angle is not small, the general solution. Okay, so what that means is that this equation here should apply for, take a snapshot. So this equation here should apply for small angles, for small amounts of amplitude, if we don't let the disk rotate very much. And so this is for small angles. And at some point, the behavior will change such that, in fact, this actually, the bottom line is this equation will always apply. Let's see, I need a better, I have to play games with whatchamacallit, Acrobat to get this thing to do the selection the way I want it. But now I just crop it. There we go. So now this one is in general true. And this is why I have put this is in the lab manual, but I've been nice enough to put it in here for you. And we'll talk about plotting it here. Let's see, this is the template. So I'm going to be uploading this, but I'm going to be a stinker, and I'm going to get rid of it. Because you guys, I've done a little work here for you. Let's see. Let's get rid of that because I want you to do some work. So that's for the, this is the elliptical integral, period versus amplitude. And then this is period versus length here for the regular pendulum. We're going to need more than this, but this is a great starting point. This is going to be another video analyzing it. Okay, so this is our background, and you should get your spreadsheet going on. We are going to be making graphs, so yeah, so you can also think about setting up your spreadsheet, but I'll make another video. I just want to get a pre-lab going on, and why don't I just copy this slide from last time. Yeah, copy this slide, and I'll just simply paste it in here. And so, yeah, PhET sim, but we're not doing a PhET sim. We're going to be using a real one, amazingly. Copy, and where did it go? Oh, there it is. And I'll paste that in just so it's there. So we're going to use a real one, but we're going to need to examine the apparatus and describe it, and then we're going to take a series of measurements with different lengths, measure the period. We're going to be taking different amplitudes and measure the period, and the dogs they're certainly on patrol. I don't know what the heck has got his attention. And here's that formula: 2 pi period equals 2 pi. There's my the older one, 1 pi, who's not a little less excitable than the 6-year-old puppy, 6-month-old puppy, who's huge. And so then notice that we're going to, first of all, this equation doesn't even contain theta in it, huh? But we still can, that's a good question. What is the equation? We're going to plot this, and we're going to look at, or graph it. Well, the easiest thing to do is that we're going to make a fit of something, because it says here L and T, but if you look at this, since it's square root of L, we sort of don't expect to see some kind of straight line, right? And we only know how to do straight line fits. Okay, so anyway, so your logbooks should be have something about, it should be the objectives. You should find out what the definitions are, how they apply to a pendulum, a simple pendulum, and a physical pendulum. Make some mention of the existence of the restoring force, this T sub x here, and of course the T, the tension, of course, is going to have also a y component, and you can see in a way how this is not a constant, well, it's a proportional restoring force, right? The more I lift it up, the greater is the restoring force. So it's not constant, which is fine. The spring doesn't have one either. So T of Y. So, you know, you can see how when I'm at the middle, there's no X component of the tension. It's just Y and of the tension and the weight. But when I pull it sideways, as theta increases, the restoring force increases. So the T sub x is proportional to the, let's see, it would be sine. So sine of theta. And this is, since when we plot sine, it's this kind of funky looking thing. But if I say that in some region, some small theta, if I can say that theta and sine of theta are equal, then I can get rid of this curvy stuff, and it makes it much easier. This is not critical for your logbooks. All you need to say is that, look, as I move it away, a component of T in the X direction appears. It points in the opposite direction of the displacement, so that's a restoring force. And that's why we're allowed to have this periodic motion, because not only do we have it when we go to positive theta, we have it when we go to negative theta. And let's see, yeah, and there's the rest. So 20 minutes, I like to keep videos at 20 minutes, and there it is. So I'll be posting this up.